Okay, so for a quick recap, in the last part we made up a mathematical description for a physical system and we called it a wave function. Then we talked about how any observable in normal life has a quantum analog called an operator that acts on this wave function. From this we got to the Schrodinger's equation, and this gave us a way to find the energy and which states have this energy. This is because Schrodinger's equation is the energy operator, normally denoted H. So the Schrödinger equation, or the energy operator, acts on a wave function phi, and what it spits out is the energy of the system E times the wave function phi. Now, I'm sorry to spout all of this off, and again, I'll be abusing terminology and skipping technical points all over, and if you can spot them, that's great, but personally, you know more than what this video aims to cover. Okay, so let's go back to Schrödinger's equation. Phi here is an example of what's known as an eigenfunction, and these are very special to quantum mechanics. Explicitly, phi is an eigenfunction for the energy operator, the Schrödinger equation. The Schrödinger equation acts on phi and spits out the energy times by phi. If a function phi is a solution to an operator for generality, let's say omega, then phi is called an eigenfunction for omega. If omega acting on phi gives a number times by phi again. Once we've got eigenfunctions for an operator omega, we can use them in a similar way to how we use the eigenfunctions for the Schrödinger operator in the last part to find the energy of a wave function. Okay, so we can write a wave function as an eigenfunction, but importantly, not every single possible wave function is an eigenfunction for your operator. In fact, the collection of all eigenfunctions for any particular operator let us build any possible wave function. We construct a state from eigenfunctions by taking the sum of these eigenfunctions, any particular sum you would possibly want. For example, let's consider psi is equal to phi1 plus phi2 plus phi3. This is a process known as superposition, a fancy name, and this will be what we will talk most about in this video. Basically, the actual state, psi, is the sum of other states, phi. And this is not a purely quantum mechanical effect. You can have it arise in classical mechanics too. But here it will have different consequences. However, we're really not going to go into how superposition arises in classical mechanics. Importantly, superposition doesn't mean any arbitrary state is allowed, just combinations of these special states. Moreover, this is one of the more interesting ideas about quantum mechanics, and it will also be responsible for most of the cool experiments we'll discuss in part 3. Now, the state of a sum of eigenfunctions is no longer an eigenfunction. However, it is still a real wave function, and you can produce it in experiments. So let's quickly show this by constructing a system from different energy eigenfunctions and showing that it's not itself an energy eigenfunction. Okay, so we have Schrödinger's equation acting on phi1 plus phi2, where phi1 and phi2 are different eigenfunctions. When Schrödinger's equation acts on phi1, it will give the energy of phi1 times by phi1. And when it acts on phi2, it will give the energy of phi2 times by phi2. Importantly, when the energies are different, we can't factorize the energy out and get the energy times by the original wave function phi1 plus phi2. So what the operator actually does on the wave function is cut it up into all of its eigenstates and tell you what they are and what the energy of these eigenstates are. I personally like to think this is why we call them operators, slicing them up and spitting all the different parts out. What does the operator tell us about the system in this case, where we don't have an actual eigenfunction, but that it is made up of different energy eigenfunctions? What it means is that when we measure the energy, we don't know exactly what it is we're going to get. If we had just the one eigenfunction, then we would definitely know the energy, but we don't. Moreover, it tells us that the possible energies we could receive are E1 or E2, and it could be nothing else. This is because the wave function we've constructed consists of only two eigenfunctions. Now, physically, you can work out the probabilities of getting the E1 or E2, and you can do this by performing the experiment over and over again, setting up the initial state, measuring, setting up initial state, measuring. In fact, the easiest thing to calculate from a wave function and an operator is the mean value from all the component eigenvalues of the wave function. This is called the expectation value, what you would expect to receive on average if you average out all of your results. But there's no way you can tell which particular energy you will get upon measuring, only the probability of getting one or the other. Now this is a big departure from classical physics, where if we set up the experiment in the exact same way over and over and over again, we'll always get the same result. Now, however, we get the exact same probabilities over and over again, but the actual value for the observable can change time to time. That is, we can never really tell what the outcome will be beyond some probability. It is part of what leads to a lot of the weird ideas about quantum mechanics. Again, I'm going to try and summarize this in quite a small statement. A state made of eigenfunctions for an observable will not have a definite outcome when the observable is measured. Rather, you will find the probability of an outcome, with the actual outcome being the eigenvalue for one of the eigenfunctions that the wave function is made up of. So it will either be E1 or E2 when the wave function is made up of phi1 and phi2. Now, to try and get this across, we'll play with an example. Let us set up a wave function as a collection of some eigenfunctions of an operator omega. So phi is equal to phi1 plus phi2 plus phi3. As I said, we don't know exactly what we will find when we measure the observable, just the probability of it being either the eigenvalue for 1, the eigenvalue for 2, or the eigenvalue for 3, which I'm just going to call 1, 2, and 3 from now on. We also know that no other possibilities can be found, because the wave function is only made up of these 3 eigenstates. When we measure the system, we will get an exact answer. It will be either 1, 2, or 3. It will not be a mix of any of them, such as we can't get 1 plus 2 or 2 plus 3 or whatever. Moreover, like I said, we won't get any other values than 1, 2, and 3. But what happens when we measure the system again without resetting it? Well, we've just measured the system and say we got 2. When we measure again, we'll always measure the same thing we just did. We will measure 2, followed by 2, followed by 2. We say that the wave function has collapsed into a state, and in this case it's collapsed into phi2. Once it is collapsed, we will never measure 1 or 3 in the system again without having to reset it. In fact, it is the collapse that is random. So the probabilities we have talked about are actually the probabilities of the wave function, the state, collapsing into one of the eigenfunctions when we measure the system. Once it is collapsed, it will remain collapsed unless we build the original state again. And it is from building the original state again and repeating the measurements over and over we can find these probabilities. Okay, so back onto building our base for studying quantum mechanics. We've talked about observables and we know that there are many observables out there. Importantly, each observable's operator will have its own collection of eigenfunctions, and each eigenfunction will define a state with a well-known value for the observable. This means that we can describe the state of any system in terms of any set of eigenfunctions, using energy, momentum, position, and so on are all perfectly valid ways of describing the system, as long as we're using eigenfunctions for some observable. Okay, but are these collection of eigenfunctions the same thing? Obviously not, otherwise I wouldn't bother mentioning it. In fact, they can be completely different. What I mean by this is that the eigenfunctions for an observable, let's say position, is not an eigenfunction for momentum. Now, we're going to play with this new language by cheating a bit and making up an example that's easy to see, but a bit physically dubious. In our example, we're going to consider this line. It is at 45 degrees to the x and the y axis, and so it can be written as the sum of both of these directions. What we want is an operator that decomposes the line into how much is in the x-axis and how much is in the y-axis. The two eigenfunctions of this operator being the x and the y direction, and the line is the wave function. But we could have drawn another set of axes, say for example w and v. With the w and v axis, we can see that the line is described by only using v, and we have no need to reference w. We no longer need the two different eigenfunctions, x and y, to describe the line. We only need this new eigenfunction, the v-axis. This shows that the two sets, x and y, w and v, are different eigenfunctions for the different operators, both capable of describing the same thing, this line. But importantly, the line is an eigenfunction for the wv operator, but it's not for the xy operator. Okay, so we've talked about collapsing a wave function, so let's collapse this line. When we measure what direction the line goes in, x or y, the line will collapse into either x or y. For ease, let's say it collapses into x. And if we measure again, we will always find it in the x direction and never again in the y direction. The state x cannot collapse into the y state. But from the original line, we could have had it collapse into the y state and never have found the x state ever again. So let's go back to the original line. This time we're going to measure if the line is going in the w or the v direction. It will always be in the v direction and never in the w. Not even in the first measurement, because it is already along the v line. The wave function cannot collapse as it is just one eigenfunction of the WV operator from the start. This example is kind of basic and a bit of a cheat example of something we will try to come back to in part 3 when we discuss the Stern-Gerlach experiment, where we will use these methods to show some of the weird aspects of quantum mechanics. Okay, so let's move on to something a bit more physical, however it might be a bit mathematically unsound. As any collection of eigenfunctions is equally a good description of the system, this is because nothing is really special in science, so we don't want to give special relevance to, say, position. We must have that the eigenfunctions for position must be expressible as the sum of eigenfunctions for momentum, just in case we personally happen to consider momentum the more fundamental object. So the x eigenstate is equal to the sum of p eigenstates. Now, importantly in this case, the sum is over every single possible eigenfunction for momentum, and each single eigenfunction for momentum has the same probability. So, if we were to measure the momentum of a particle with known position, we would have that it could be any possible momentum. This holds the other way around as well. If we had an exact momentum eigenstate, then it must be the sum of all possible position eigenstates. This can be understood as the basis of the uncertainty principle. We can't know both position and momentum of the system, and this is because of wave functions collapsing. If we were to measure position, we will disturb the wave function, collapsing it into a position eigenvector. This is made up of infinitely many momentum wave functions, so the momentum can be anything at all. This means that we have an infinite uncertainty in the momentum of a position eigenstate. Infinite uncertainty when we know the exact position. If you know the exact position, you have no idea what the momentum could be. The best you can do in this case is know them both to an accuracy such that the uncertainty holds, that the error in position times the error in momentum has to be greater than or equal to some constant. That is, the error on your position measurements and the error on your momentum measurements have to obey the uncertainty principle. We will talk a lot more about this in part 3, where we will use this to explain the double slit experiment. The other two effects that we will examine are the Stern-Gerlach experiment and electron diffraction off a crystal lattice. If you have made it this far, thank you a lot for listening, and let me know if you have any comments or questions.